grade 12 learners, welcome to today's subject lesson. My name is Sibusiso Shongwe. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center, and it's broadcast by Pagama Research and Development. Remember our WhatsApp interactive number 064 748 8913 064 748-8913. You can use that number to interact with us. Right, today we are looking at a continuation of last 2 weeks' lesson where we were interpreting sketched functions, and there were some parts of that lesson that we did not complete. So we are going to start there today, complete interpretation of sketched functions. We'll be looking at inequalities and graphs. We'll also be looking at the nature of the roots graphically. And then from there, we'll touch on the sketching of a third-degree function or the sketching of a cubic function in differential calculus. Right, to start off, let's look at the outcomes. By the end of this lesson, you should be able to solve inequality problems using graphical approach only, solve nature of the roots problems using graphical approach only, solve nature of the roots problems in cubic functions using graphical approach only, use the factor theorem to find the roots of a third-degree polynomial, sketch the graphs of a cubic polynomial from a given equation. You can refer to the CAPS document on page 32, 44, and 46 for what we're going to be doing today. You can also refer to the exam guideline published in 2021 on page 6 and on page 7. Right, starting off, we're going to go back to the notation. We are explaining now the notation that we need or that we should know for us to be able to interpret the notation questions in graphs. Right, the first one, we are looking at values that are excluded. There are 3 ways of representing values that are excluded. We can use our round brackets, or we can use our less than or greater than sign, or we can use an unshaded circle there to indicate on the graph that these are the values that are excluded. For values that are included, we can use square brackets, we can use less than or equals to sign, or greater than or equals to sign, or use a shaded oval there. Now, if the first value is excluded and the last value is included, you can use a round bracket for the first value and a square bracket for the last value that is included. And then values are excluded because of restriction, you use that. Values are included because of restriction, you use a square bracket. Right, we go back to comparisons. Remember, the idea with comparisons is to look at 2 functions and to compare them, whether or where one of the function is above or whether the other function is below. You're going to be looking at that particular region where one function is above and one function is below, or rather the 2 functions are equals to each other. Now, to start off our comparisons, we look at f of x equals to g of x. That is where the 2 functions are equal. That is the point of reference. You always start there. You always start where they are equal, and from where they are equal, they are then going to overlap. You need to study that overlap and be able to determine the region in which that overlap occurs according to the question that they want you to answer. Now we have f of x above g of x. That is where f should be above g. F of x greater than g of x. It means f is above g. And f of x less than g of x, it means f is below g. The last one, f of x minus g of x is equals to 1. It can be any other number, learners. It's not only fixed at 1. It can be any other number in this case. Now, this just means f is above and g is below, and the distance between the two is equals to 1 unit. So you're going to check the region in that particular graph, or the value of x in that particular graph, where f is above and g is below, but the distance, the vertical distance between them should be 1 unit. Right, let us explain combinations. Remember, with comparisons, I said you're going to start where the graphs are equal, and then you're going to check on the left-hand side of where the graphs are equal, going to check in between the 2 points of intersections if they are 2, and then you're going to check on the right-hand side. We will be moving from left to right when we analyze these graphs. But with comparisons, with combinations now, it's different. We are now looking into combinations. With combinations, it's different. You're looking at two functions. You want to combine these two functions. And in order to do so, you can use a multiplication or division. So now we're going to check the signs. If you are to have two signs that are negative, if you multiply them, you get a positive sign. If you have two signs that are positive and you multiply the two operations, you're going to get a positive sign. If you have two signs that are now different, if you multiply them, you're always going to get a negative sign. So that is how we combine the functions. We're going to check where the function is negative or whether the function is positive. How are we going to look at that? We're going to start with the reference f of x times g of x is equals to 0. That is the reference of combination. Remember, with comparison, going back, with comparison, the reference was when f of x was equals to g of x. Now, but with combinations, the reference is when f of x times g of x is equals to 0. This is where either one or both functions are equals to 0. It's either where f of x is equals to 0 or where g of x is equals to 0, or where both of them are equals to 0. Remember, f of x is equals to 0. By f of x is equals to 0, we mean y is equals to 0. And for y is equals to 0, this would be your x-intercept. So basically, your point of reference with combinations should be the x-intercept of one of the functions or both of them. So this means the x-intercept of f, or the x-intercept of g, or the x-intercept of both f and g. That is the point of reference. Now, moving away from the point of reference, we multiply f of x and g of x, and we get that it's greater than 0. It's positive. So they are telling you that the two graphs should have the same signs. It means that they should either be both positive or both negative, because if you combine two negative signs, you get a positive. If you combine two positive signs, you get a positive. So basically what we're going to be doing is we're going to be combining the two functions, but we need to check where the other is positive and where the other is negative. By saying f of x is positive, we are trying to say that the region where f is above the x-axis. So when both graphs are above the x-axis, or when both graphs are below the x-axis. Now, if you look at f of x minus g of x, or times g of x is less than 0, one graph should be above and the other graph should be below the x-axis. Now, the same would hold, or that idea would still hold for quotients. It will still hold for two functions divided together. The only catch here would be the restriction, because here we have now a fraction. It means that the denominator must not be equals to 0. So you need to note that a restriction that g of x must not be equals to 0. So you're going to check where g of x is equals to 0, and you make sure that you restrict that particular value when you find your solutions. It goes on to x times f of x is greater than 0. We are now looking at the combination between a function f of x and some value of x. So we are looking at the x-axis. So we are now, if it's positive, we are looking at the positive x-axis and the positive graph of f, or where f is above the x-axis. But if it's less than, you are looking at different signs, either negative x-axis and positive graph of f, or graph of f is above the x-axis. You can move on to derivatives now that you've done calculus. We have f of x times f dash x is greater than 0. Here we are looking at the region where the graph of f and its derivative, or the gradient, is positive, where both of them are positive or where both of them are negative. We are now comparing the graph of f together with its gradient. You can do the same as well with g of x times f dash x is less than 0. Here you are looking at where the graph of g and the graph of the gradient of f have opposite signs. You are looking at where they have opposite signs because it says here less than 0. Right, let us go to the application now. Let us go to the application. We are going to start off with comparisons. How do you identify comparisons? We are comparing two functions, f of x and g of x in this case. So we're looking at a region where f of x is greater than g of x, or f of x is less than g of x, or where f is above and g is below, and we're looking at that vertical distance between them. Now, to start off here, we are going to identify the points of reference. It's very, very important that you know the point of reference because it helps you know where to start. Now, the point of reference in this case, because it's a comparison, the point of reference will always be the points of intersections. So what I do now is I'll draw vertical lines on my point of intersections. I have 2 points of intersections between these two graphs. That's where I draw my vertical line. So which means that my reference here would be, or the critical value here would be -3, and another critical value would be -1. We're going to focus on the values of x. Remember this, once the values of x for which y exhibits a specific behavior. That is what we are looking at. We are looking at the values of x for which y would exhibit a specific behavior. Now, if you look at these two, I've identified my critical values. In this case, my critical values lie on the point of intersection. So now what I'm going to do is I'm going to check from left to the first point of intersection and check which graph is above and which graph is below. And then I'm going to check in between the 2 points of intersection which graph is above and which graph is below. And then I'm going to check on the right-hand side of the point of intersection whether which graph is above and which graph is below. Now, let us first start by labeling these graphs. The straight line is called G. So this is G, and the parabola is F. That's F. So this is F, this is G, and that's F. Now, let's start by checking values from -infinity to the first point of intersection. We are moving from left to right. Now, if you check from -infinity to -3, from -infinity to -3, you can see that G is above. You can check here, this is the graph of G. The graph of G is above the graph of F. So the graph of F is below. That's not where we want. Remember here we want where F is above or on G. We want where F is above or where F is exactly at G. So when we look at now, we started with this region from -infinity to -3, and we don't find a solution. Now we're going to check in between the 2 points of intersection. In between the 2, you can see that F is above and G is below. So that is where our solution would lie. But we don't stop there. We continue and check on the right hand side. If we check from -1 to infinity, G is now above and F is below. So our solution would lie in between the two critical values. In this case, our critical values are -3 and -1. So we have that our solution lies in between the two critical values. Remember, there are many notations that one can use to write this solution. One can write it this way: x an element of, because it's included bracket, remember we looked at the notation, -3 to -1. So that is basically where we find the solution. We find the solution between -3 and -1. If we want to write it in inequality notation, we will write it using x greater or equals to -3 but less than or equals to 1, that compound inequality. But if we want to write it using interval notation, then x is defined in the region between -3 and -1. Right, moving on to the second one. The second one, the examiner here tried to trick us a bit by subtracting or putting g of x to the other side. So you can see that this is f of x minus g of x is less than 0. This is not a combination question, because with combination you use only multiplication and division. But now here we have a subtraction sign, which means that now if we can transpose a g of x, we'll get that f of x is less than g of x. So we are looking at the region where f is below and g is above. That's what we are looking at. We are looking at a region where f is above or where f is below. F here, f is below g. That's what we are looking at. We are looking at a region where f is below g. That's what we are interested in. Now, we're going to start on the left-hand side from -infinity to -3. If you check from -infinity to -3, f is below g. And in between -3 and -1, f is above g. That's not where we want the solution. So we are interested in this part here. And then we check from -1 to positive infinity. You can see that g is above and f is below g. So we're also looking at this particular region. So the region of interest in this case is when x is less than -3 or when x is greater than -1. That is where we get our solution. If you want to write it in interval notation, you can write it as x an element of, we go from -infinity to -3, we unify the two, and then we can go from -1 to positive infinity. That's how you can write it when you use interval notation. So to save time, moving on, I'll only be using the inequality notation. Right, let's look at the last one, the third one. G of x minus f of x is equals to 3. Remember, I said here, the idea is if you have a plus or a minus, you know that you are comparing these two functions. But in this case, we have a value 3 instead of 0. What does that mean? If there was a 0 here, we were going to transpose f of x, we get g of x is equals to f of x. That's the point of intersection. But now the distance is equals to 3. So we are saying g is above f and distance between them is 3 units. The distance between them is 3 units. So we have to look at where g is above, f is below, and the distance between them is 3 units. Now, if we can go to this graph and check the y-intercept of the straight line, the y-intercept of the straight line is given by 6. And check the y-intercept of the parabola, from the given equation. From the given equation, if you put x to be equals to 0, you would get that f of 0 is equals to 3, which means the y-intercept of this particular parabola would be 3. So this value here is 3. So the value of g is 6 and the value of f is 3. G is above with 6, f is below with 3. Now, if you get the difference between the two, 6 minus 3, you're going to get that the distance becomes 3 units. But we are looking for the value of x. This occurs here. We are looking for the value of x where g is above f and the distance is 3. So 6 minus 3 gives us 3, and that occurs when x is equals to 0. I repeat, in this type of questions, we are interested in the values of x for which y exhibits a specific kind of behavior. So how are we going to get that behavior? The behavior of y would be given in the question, and the behavior of y can be subdivided into two categories. The behavior of y can be subdivided into comparisons and also combinations. That is the behavior of y. But our interest here in this case is to find the value of x for which y exhibits that specific behavior. Now, moving on, we are looking at now the combinations. If you check here, we are multiplying f and g. We are also dividing f and g. So we are looking at now the combinations. Now, the idea with combinations is you're going to start with where the graphs intersect the x-axis. That would be your reference point. Where f intersects the x-axis, where g intersects the x-axis, or where both of them intersect the x-axis. Now, if you check here, you have the first point here. Both of them intersect the x-axis at that particular point. So that would be your critical value, minus 3. And then moving along the graph, you see that g, because it's a straight line, it will only have one x-intercept. But with f, there's another x-intercept here. So you're going to, if I just continue with this here, I'm just extending that, extrapolating that line. If I draw a vertical line here, I will have another point of reference. So if you check here, the points of reference are different as compared to the one on comparisons. Here, the points of reference or the critical values would be where the graphs cut the x-axis. So you can see that both of them cut the x-axis at minus 3, and both of them cut, f cuts the x-axis at 1:0. So that's what we are interested in. That's where we're going to start. Now, let's check here. The first question. The first question here wants where f times g is greater than 0. Greater than 0 means positive. And the only way of getting positive here is that if f is positive and g is positive, if you multiply these two, you're obviously going to get a positive, which is greater than 0. Alternatively, still on operations from grade 9, if both the signs are negative and you are multiplying them together, you are going to get a positive, which means that it's greater than 0. So you are interested in where both graphs are positive. Where are they positive? With respect to the Cartesian plane, both graphs are positive when they are above the x-axis, and they are both negative when they are below the x-axis. So we're going to assign those signs to the graphs. I'm going to start with the graph of g. If you look at the graph of g, this portion of the graph of g between minus infinity and minus 3, this particular portion is below the x-axis. So I'm going to assign negative signs there. But now, at minus 3, that's where it's exactly at the x-axis. Greater than minus 3, this graph is now above the x-axis. I'm looking at the linear graph. It is at the x-axis until positive infinity. Now, let's look at the graph of f. The graph of f from minus 3 to 0, you can see that there's a portion of that graph that is below the x-axis. So there's a negative here. Sign of this graph is negative. And then at minus 3, the graph is exactly at the x-axis. But moving on from that, you see that now this graph is above the x-axis. So I'm going to put positive signs there. Up until 1, where the graph now is exactly at the x-axis. And then here, it then goes below the x-axis. Now, that is where I'm going to start. So, in order to write down my solution, I'll take my critical values. My critical values in this case, I have minus 3, and then I have positive 1. Those are my critical values. And then I'm going to look, because I'm multiplying the two, I'm going to focus on the product. Remember, at the point of reference, the product of the two is 0. Now, let's check from minus infinity to minus 3. We need to check what the product would be. We need to check on this region here. On this region here, what would be the product? We have G is negative and F is also negative. So both graphs are negatives, and negative multiplied by negative gives you a positive. So it's positive this side. And then from there, let's look at the values in between minus 3 and 1. We want to check between minus 3 and 1. So we are interested in this region between minus 3 and 1. If you check, the signs of both the graphs are positive. So positive multiplied by positive, we get a positive. And then we move on to values that are greater than 1. You can see that the straight line is positive, but the parabola is negative. So positive multiplied by negative, in this case, gives us a negative. So now, let's check what the question wants from us. The question wants from us where both are positive. So we are looking at where the combined effect in this case is positive. Now, if you check, that would occur here and also this side. So that would occur when x is less than minus 3, or when x is in between minus 3 and 1. So it occurs when x is in between minus 3 and 1. It also occurs when x is less than minus 3. Someone might say, what if, say, I just write this as x less than 1? If I write it as x less than 1, I write it as x less than 1, because I can see that going from, if I move from 1 to my left-hand side, I get 2 positive signs. This would not be correct. It would not be correct because at minus 3, the graphs are equals to 0. They are not positive. At minus 3, the graphs are positive. They are not positive. They are equals to 0. So we need to exclude minus 3. In order to make this a correct solution, would say, but x cannot be equals to minus 3. So if you exclude minus 3, then the second solution would also hold. So we have two different, or rather two answers that are represented by different notations or different ways, but both of them are correct. Right. Moving on, grade 12, we are looking at now f of x divided by g of x is less than or equals to 0. So we want where the combined effect of the graph. So we want either positive divided by negative, because we know when positive is divided by negative, we get less than. When negative is divided by positive, we still get less than. So that's what we are looking at. We are looking at one graph above and the other graph below. But now the key aspect here is that there is a denominator g of x. So we have here a restriction, and our restriction is that g of x must not be equals to 0. That is the restriction. The denominator must not be equals to 0. Now, what we need to do is we're going to check now where g of x is equals to 0, and then we're going to exclude that value of x. Now, so we're looking at the x-intercept of the graph of g. The x-intercept of the graph of g is given by -3. So we are saying x cannot be equals to -3. That is what we need to keep in mind when we derive this solution. Right, I'll come back again to this one. I'm going to still draw my number line, putting my critical values -3 and +1. In this case, we have that there is less than or equals to. So the values are included. So I'm supposed to include the values. However, because of the restriction, I'm not going to shade -3. This one, I'm going to include it because it says values must be included. However, there's a restriction. Right. Now, from here, what I'm going to do is I'm going to check the graphs from -3, from -infinity to -3, check the signs. If you check from -infinity to -3, both graphs are negative, which means I'll have the positive. But the quotient here is 0. Also here is 0. I'm looking at the quotient. The quotient here would be positive between -infinity and -3. Now, between -3 and 1, if you look at it between -3 and 1, you can see that both graphs are positive, and the combined effect in this case would be positive. And then if you look at values from 1 until positive infinity, you can see that the straight line is above the x-axis, but the parabola is below, so this would be negative. So now, according to the question, we want the combined effect when the two graphs are negative. So we are interested in this side of the solution. So it occurs when x is greater or equals to 1. That is where we get the solution, where f of x is divided by g of x. Remember, if this was not restricted, if for an example this was f of x times g of x is greater or is less than or equals to 0. If it was that case, then we were going to have x is greater than or equals to -1, but we were supposed to also include 3. Or we're going to have or x is equals to -3. But now, because -3 was restricted, we take it out of that solution set. Right, moving on. Now we are looking at, it's a combination as well, but in this case we are looking at now the x-axis. The combination of the x-axis and the function of f. Now, which means that here we're going to start with our reference point. Remember, it's combinations. With combinations, the reference point or the critical values would always be where one graph is at 0 or when both graphs are at 0 or where they intersect the x-axis. So now, if you check here at -3, the graph of f intersects the x-axis. So this would be our reference point. And then when you check also at 1, x is equals to 1, this is where the graph of f is equals to 0. However, we also need to look at where the x-axis is given by 0, where the value of x in the x-axis is given by 0, and that occurs at the origin. So we're going to have that now. We have an additional point of reference here. That is where the x-axis is equals to 0 in this case, which means that now for this one, we have 3 points of reference, -3, 0, and 1. Values are not included. We are multiplying the 2x times f of x, which means that we are looking at now the product. Obviously, the product here is 0 at the critical values. The product is 0. The product is 0. Then now we need to then draw, or rather put our signs on the diagram. How are we going to do that? We're going to first look at the graph of f, where the graph of f is positive or where the graph of f is negative, above the x-axis or below the x-axis. If you check from minus infinity to minus 3, the graph of f is negative. So put negative signs there, but here it is positive, positive, and then going down here, it's negative. That is the graph of f. And then we need to compare it with the x-axis. X-axis are negative this side. X-axis, x values are negative this side. The x values are equals to 0 at the origin. X values are positive this side. So now when we compare the two, let's now start with our comparison or the combination. In this case, we are going to combine from minus infinity to, remember we drew those vertical lines. So when we start, we're going to start from the left of the from the left hand side to the right hand side. So we start from minus 3 or minus infinity to minus 3, and then we check from minus 3, between minus 3 and 0, and then we check between minus 3 and 1, and then we check from 1 to positive infinity. So from minus infinity to minus 3, you can see that both the signs are negative, which means that the combined effect would be positive there. And then we check from minus 3 to 0. You can see that from minus 3 to 0, in between here, you can see that f is positive and the x-axis negative. So the combined effect would be negative. We check again between 0 and 1. Between 0 and 1, you can see that in this region here, there are positives. F is above the x-axis as well as the x-axis is positive. So we're going to say that now the combined effect would be positive. If we check from 1 up until positive infinity, we're going to focus on this region here now. If you check there, you see that the x-axis is positive, but the graph of f is negative or below the x-axis. So the combined effect would be negative. So we are looking for our answer where the combination is positive. So it occurs when x is less than minus 3 or when x is in between 0 and 1. So that is where we get the solution set to this higher order question. Now, let me explain this again. We are going to focus on our points of reference first. Remember, this problem, we've identified it as a combination problem because the sign between the two functions or between the two entities that we are comparing is a multiplication sign. So we are combining them. So we're going to start with the critical values. Where do we get the critical values? We get the critical values where the one graph or both of them are exactly at the x-axis or the x-intercept of those particular graphs that are compared. So we've identified that our critical values are minus 3 because it's the x-intercept of f, 0 because it's where the x-axis is at 0 or the values of x are given by 0, and then 1 because that's where the value or that's where the graph of f intersects the x-axis. So that completes what we wanted to do in this case for comparisons and combinations. I'll summarize it briefly now. With comparisons, we are going to be looking at two functions. We compare them whether one is above or below the other. Where do we start? Our critical values would be where they intersect. And then with combinations, we are now looking at the signs of the two graphs. So we need to then check where they are cutting the x-axis, or we look at the x-intercept as the point of reference. It's the x-intercept of one graph or the x-intercept of both the graphs. Right, moving on. Now we want to determine the nature of the roots graphically. Grade 12, here what we are looking at. Remember, with combinations and comparisons, we were looking at the values of x for which y exhibits a specific behavior. So we were focusing on x. What does x do as y behaves the way in which they gave us in the question paper? So we were focusing on the values of x. However, now with the nature of roots, we are going to focus on the values of y, for which x exhibits a specific behavior. So we are now going to be looking at the vertical axis, or the values of y. We are going to be given the behavior of the roots, the behavior of x, and then from the behavior of x, we're going to check how y changes, or we're going to look at how y behaves as x exhibits a specific behavior that would be given in a particular question. So we are talking to nature of roots. We want to determine the nature of roots graphically. With me here, I've summarized this using the parabola. We're going to start with the parabola. But it does not mean that these questions are only limited to parabola. You can determine nature of roots in a parabolic function, in a linear function, in an exponential function, in a hyperbolic function, and in a cubic function. This can also be extended to trigonometric functions. You can be able to determine the nature of the roots there, as long as you understand the fundamentals of determining the nature of the roots. Now, it starts with the parabola, because with the parabola, we have the discriminant that assists us with the nature of roots. Now, and it's easier to determine nature of roots if you have parabolic functions. Now, if you check the first graph here, I'm going to focus on the turning point. I'm going to focus on the turning point. If you look at the turning point of the first graph, it does not touch the x-axis. So we say that this graph exhibits non-real roots, because there is nowhere in the graph where the graph cuts the x-axis. So we say it has no roots. That is for a concave up graph. You can still do the same for a concave downwards graph. Now, if you move the graph just from where it was, just move the turning point to the x-axis. You see now that it touches the x-axis once. We say it has equal roots if it does that. And then if you continue moving the graph below the turning point, you're now going to see that it cuts the x-axis twice. And then we say that it has two roots in this case. It will have two roots. That is how we're going to be determining this nature of roots. If you move the graph up and down, you can see that there's somewhere where the graph does not cut the x-axis. There's somewhere where the graph cuts the x-axis once, and there's somewhere where the graph cuts the x-axis twice. You can do that with a concave up or a smiling parabola. You can also do that with a frowning parabola. Right. Explaining nature of roots using the graphical approach. Now, I'm going to explain what you need to do if you want to use graphical approach to explain the nature of the roots. I'm going to explain what happens here. Now, what basically happens in these questions is that you're going to check where the variable of interest, for an example, suppose that R is the variable of interest. Suppose that R is the variable of interest. If we are interested in the values of R for which the roots would exhibit a specific behavior. Now, there are two types of questions that exist. Type 1. Type 1, R will be the y-intercept. For example, f of x is equals to x squared minus 4x plus, say, for argument's sake, say plus 4x. Let me rewrite this. F of x is equals to x squared, maybe plus 4x, and then minus r, for argument's sake. If you check now, R is where we normally have our y-intercept. That is where R is. That is where we find r. So that would be type 1. R would be the y-intercept. And if r is the y-intercept, you want to know what happens to the value of r as the roots behave in a specific manner that would be given in the question. So what you're going to do here, if r is the y-intercept, we're going to move the graph up and down depending on the question asked or the questions asked. So if r, or the variable we are interested in, is the y-intercept, we are going to be interested in moving the graph up until we get to the desired roots. But there is also another type, type 2. R is the value of y, or the value of f of x. For an example, you have now, instead of having f of x, you have x squared plus 4x and then minus, say, 8. Minus 8 is equals to r. You see now, r lies where we had f of x, or where we had y. So here we are going to be moving, we are going to be moving a horizontal line, y is equals to r, up and down, depending on the questions asked. So that is type 1 and type 2. How are you going to pick it up? You're going to check the variable would either be the y-intercept, or the variable would be where y, or the function value was at. So you're going to then be moving depending on what you are given. It's either you move the graph up and down, or you move the horizontal line up and down. Now, as I explain this concept, I'll show you that it's more advisable, or it becomes a bit easier, if one moves the horizontal line. That would be the generic approach. I would be showing you how we can generalize, because type 2 can also accommodate type 1 questions. But I'm going to show you how that can be done. Right, let us look at the first example. The first example, if you check now where k is, you see that k is where y is supposed to be, is the y-intercept. And the y-intercept of this graph is minus 8. I can just put it in the graph, minus 8. So you can see here that k is actually the y-intercept. So I said here, if it's the y-intercept, then what should we do? We move the graph up and down, depending on the questions asked. So which means that with these questions, we're going to be moving the graph up and down. But I'll later show you that even if you transform this equation and make this a type 2 question as opposed to a type 1 question, can be able to move a line. Now, let's start with the first one in this case. The first one, they said it has equal roots. Now, the advice that I'll give you here, grade 12s, is that you're always going to take the graph that is given. You are interested in the turning point first. Take the graph and move it to the x-axis, or move it in such a way that the turning point is at the x-axis. So I'm going to move this graph up here so that I have the turning point here. I start here, I have the turning point there. That should always be where you start. So if the turning point is there, I'm checking. Remember, k is the y-intercept. I need to check what happened to the y-intercept. What did I do? I moved from minus 9 to 0. So I added 9 to the y value of the turning point, which means I can add 9 as well to the y-intercept. I'll get that this is positive. 1. Now, if you look at it here, it's where I say it's in a standard position. I usually say it's in the standard position when it's on the x-axis. So I have the graph now on the standard position. Then I can check the questions when the graph is at the standard position. The first question says, for which values of k will this have equal roots? Remember, for equal roots, what did we say? We said that the graph should cut the x-axis once, or the turning point of the graph should be on the x-axis. So that occurs when the y-intercept is equals to 1, because k is the y-intercept, and the y-intercept in this case is equals to 1. And then the second one says where it has non-real roots. We are looking at it now where it has non-real roots. So now what we're going to do is we're going to move the graph such that it does not touch the x-axis. Non-real means it does not touch the x-axis. So what should we do with the graph? We should move the turning point of the graph just a bit up. So if you just move it up, just slightly up, you'll see that now the turning point would now leave the x-axis and no longer touch the x-axis. And now we are interested in what happens to the y-intercept. Remember, as you move the graph, we are interested in what happens to the y-intercept. Now, when you move this graph just a bit up, what happens to the y-intercept? It also moves just a bit up. So we're going to say immediately when k is greater than 1, then the graph will not touch the x-axis. So as the value of k grows bigger than 1, the graph does not touch the x-axis. So we say that it has non-real roots. You can see here that it has there is no place where it touches the x-axis. Remember what I said with these questions. I said you are going to be looking at the values of y for which x exhibits a specific behavior. Right. Moving on to the last question, it has 2 real but unequal roots. Now, if you check, if you just move the turning point just a bit below, if I move the turning point here just a bit below the x-axis, what happens? The graph is going to cut here, the graph is going to cut there. So it has now 2 x values or 2 roots. Also, when I continue moving down, the graph possesses 2 roots. Even this one possesses 2 roots. So when I move the graph just below the x-axis, then it will have positive, or it will have 2 different roots. Now, I'm asking myself, what happens to the value of y as I do that? Now, if you check here, what happens to the y-intercept? As I move, I just need to go just below 1. The y-intercept just goes below 1, and then I would have those specific roots. Right, that is the first part. I'll come back here. I want to transform this. I want to transform this particular question and show you that it can also be converted to a type 2 question, but I'm moving on quickly. Now, if you check here with this one, the value of k now is where y was. So I'm going to now be moving a line y is equals to k. I'm going to be moving a line y is equals to k, where k can be any number. So now I'm interested in moving the line. What I like about moving the line is that you don't focus on 2 things. Remember, when I move the graph, you're going to focus on the movement of the graph, and then after focusing on the movement of the graph, you focus on the y-intercept. What happens to the y-intercept as I move the graph? So there are 2 things: movement of the graph, movement of the y-intercept. But now, in this one, you're going to be focusing on only the line, where the line cuts the graph once, where the line cuts the graph twice, or where the line does not cut the graph. Now, if you check here, they said it has equal roots. The first one says equal roots. I'm interested in the line y is equals to k. Now, what you do here, grade 12, is that you're going to start with your line. You're going to start with your line below the turning point. So this would be my line. I'm just going to put it at the turning point first. So when it's at the turning point, what would be the value of k here? Here it's y is equals to minus 9. So also k is minus 9. That is where, when it's at the turning point. So at the turning point, you see this line cuts the graph once. So you have equal roots because it cuts once. So if you have equal roots, you're going to say you will have equal roots when k is equals to minus 9. Non-real roots, if I move the graph just below now, just below the turning point, you see now that the line is not touching the graph. So I'm going to say that if k is less than minus 9, then I'll have non-real roots. However, if I want to have two unequal roots, if I start now and move the line up, if you check here, the line cuts twice. If you check here, the line cuts twice. If you check anywhere as I go up, the line is cutting twice, which means that here now I have two roots that are not equal, but that occurs when k is greater than minus 9. So that is basically what we have. That is basically what we have here, grade 12s. So let's check, because this question is much more easier because we're just moving the line, and we check what happens as we move that particular line. Now let's go back to the one that we did before. Let's go back to this one and check whether we can transform this in order to look like the one that we did, that we just did, where we can move the line. Let's check if I can have this equation. It's x squared minus 2x. If I can transpose k, I would have minus k. And for this equation to look like the original equation, I would subtract 8 this side, subtract 8 this side. You can see now that this is now f of x. So our f of x is minus k minus 8. So we are moving a line, y is equals to minus k minus 8. I'll only do one of this. Let me just choose one. I'll choose B. I've transformed the equation. I'm interested in it where there are non-real roots. There would be non-real roots when my line is here, just below, when my line is just below the turning point. What is the identity of my line? My line is y is minus k minus 8. So I'm looking at it where this line, minus k minus 8, is below the turning point. So I have that minus k minus 8 should be less than minus 9. That's what it should happen for this line not to touch the graph. So if I transpose minus 8, I have minus k is less than minus 1. If I divide both sides by minus 1, k, obviously it's an inequality. So when you divide by a negative or multiply by a negative, the direction changes. So it's k greater than 1. So if you compare it with this one, you get the same type of solution. But in this case, you are using a different method. You are using transformation. You are transforming this equation that has been given in order for it to look like the original equation, so that you just move the line. Right, moving on. Remember here we were just moving the line and we were able to get the behavior of y. So it continues also here. Remember the y-intercept of this is minus 8. It continues here to say x squared minus 2x minus 8 is equals to k has two positive roots. It has two positive roots. Now, when will this graph, if you check here, k lies on the where f of x was. So we have f of x is equals to k, because k lies where we had f of x in the original function. So we are moving a line y is equals to k here, but we are interested in it where we have two positive roots. Now these questions f, g, and h are variations of the original questions that we had. I just increased the order. These are pitched a bit up in terms of cognitive levels. They are not the same as the ones that we just worked out. I pitched them just a bit up in terms of cognitive levels. They are a bit challenging in this case. We're looking for two positive roots. Now, remember, it starts here. Our line starts here where I have equal roots. If I move it up here, I have two roots, and both roots are positive because they both lie on the positive x-axis. Also here, I have two roots, and both the roots are positive. When I'm at now the y-intercept, I have two roots as well, but one root is equals to 0. Just above the y-intercept now, you see one root is negative and one root is positive. Moving up, just above the y-intercept, you can see that I now have a negative root and a positive root. Now, I want this where both roots are positive. Where does that occur? It occurs when you look in between. Check the lines that I drew between the y-intercept minus 8 and the turning point minus 9. The lines that I drew there, both of them are, or rather, in all those lines, the graph has two positive x-intercepts. So what I'm going to do here, it will have two positive roots if k is in between, let me write it here, f. If k is in between minus 9 and minus 8. When k is above the turning point but below the y-intercept, that is where I'll find those roots. Now another one, variation, roots which differ by 6. What is y when the roots differ by 6? You are given the values of x, you want to know what y is when x exhibits that specific behavior. I'm looking at G now. We're saying the roots would differ by 6. Now, if you check on the x-axis, if I put my line here, what is the difference between these roots? It's 4 minus minus 2. 4 minus minus 2. This is 4 plus 2, which is equals to 6. So these roots differ by 6 when I'm at the x-axis. The roots differ by 6. What is the value of y at the x-axis? The value of y in this case is equals to what? 0. That is where the roots now differ by 6. Now another variation, roots differ by 2. Roots differ by 2. This can be a level 3 difficult question. Level 3 difficult, this one. If you look at this now, they want where the roots differ by 2. It's a bit tricky. But if you check the y-intercept and check the axis of symmetry. Remember the axis of symmetry is x is equals to 1. What is the value of x at the y-axis? When y is minus 8, x is equals to 0. So you are moving from here 0 to 1. Which means that if you move from the axis of symmetry, remember this is symmetrical. The parabola is symmetrical about the line x is equals to 1. Which means that the points on the left or on the right, on the left are equidistant to the point on the right. Because I'm moving from the axis of symmetry. The distance from the axis of symmetry to the left and the distance from the axis of symmetry to the right should always be equal. So if I move from the y-intercept to the axis of symmetry, the value is 1. If I move from the axis of symmetry to that extreme point there, the value is also 1. So if I put my horizontal line here exactly at the y-intercept, what would be the distance? The distance would be from the y-intercept to that which is 1, and from the y-intercept to that which is 1, and from that axis of symmetry to that extreme point is also 1. So the distance is 2. The distance is only 2 when k is equals to minus 8. The distance would be 2 when k is equals to minus 8. Right, we move on. Now I have a short activity here. I'm going to give you 3 minutes to try and work out the solutions for A and B. We'll only focus on A and B. we are now looking at an exponential curve, and we want to determine the nature of the roots there, so that we know that it's not only limited to the quadratic curve or the parabola. So I'm giving you 3 minutes to work that quickly, and your time starts now. Hello and welcome back, grade 12s. Right, I've given you 2 questions to work with. Those questions are on this exponential curve. I just want us to run quickly through them so that we move on with the other concepts that I need to work with you, or to work out with you. Now, we are given the y-intercept of this function is 0:4, which means that we have the value 4 there. And then if you check the first one, we are given 2 to the x plus 1 plus 2 is equals to r. Now, if you check 2 to the x plus 1 plus 2, it's our f of x. So it means that here we are having f of x is equals to r. So we are moving the line y is equals to r. What are the desired outputs there? We are interested in where the graph would have non-real roots. Now, what we're going to do here, because we want the graph to have non-real roots, we are going to be moving our horizontal line f of x is equals to r, such that that particular horizontal line does not touch the graph. So if it's at the asymptotes, the horizontal line does not touch the graph. But if it just goes above the asymptote, then it starts touching the graph once on the negative x-axis. So if you are at the asymptotes and also below the asymptotes, if you start at the asymptote and below it, then that particular line is not going to touch the graph. So we are interested in y, what would be the value of y at the asymptote and below it? It would be r is less than or equals to 2. R is less than or equals to 2. So it's either the horizontal line is at the asymptote or below the asymptote. That's where you'll have the horizontal line not touching the graph. Now, f of x is equals to r has negative root. So we are interested in it where it has negative root. So here they simplified it for us. So we are moving a line y is equals to r. But we are interested at where the line has a negative root. So we are interested in where it touches the graph once. Where it touches the graph once. So now if you move just above, if I check from the graph, if you move just above the asymptote, you see it touches the graph once on the negative x-axis. As you go up, it touches the graph once on the negative x-axis. But when you reach the y-intercept, then it touches the graph at 0, or it touches the graph where x is equals to 0 on the y-axis. So we are interested where it touches the graph on the negative x-axis. Where does that occur? It occurs when you are in between, just above the asymptote and just below the y-intercept. The graph touches on the negative. Because if you are to continue with your lines here, you see that now it touches the graph on the positive x-axis. Touches the graph on the positive x-axis. And we are looking for the negative root. So we get the negative root when the graph is just above the asymptote and just below the y-intercept. So that occurs when r is just above the asymptote and just below the y-intercept. So that is the solution set that you were actually looking for. Right, moving on, creators. Now, this idea can be carried on to cubic functions. I'm not going to stay long here. I'm just going to touch on this slightly because I want us to move to sketching a third-degree graph. So I'm not going to waste a lot of time on this. I'm just going to explain the concept here without answering any of the questions. You are interested now, if you put the line here, check if I put the line there, extending or extrapolating the graph, if I put my line there, how many times does the graph touch? It touches twice. So I have 2 roots or 2 positive roots. Also at this turning point, the line touches the graph twice. So if they are looking for 2 unequal roots, because there are 2, if it's 2 unequal roots in this case, you are looking at where the line touches the graph twice. Where does it touch the graph twice? When k is equals to 18 or k is equals to -9. Remember, we are looking at the values of y for which x exhibits a specific behavior. What is the behavior of x according to this question? It has 2 unequal roots. Now we are talking about 1 root. If you move this up, just up a bit, just above the turning point a bit, it touches only twice. Or just below the turning point here, it touches only once, I should say. If it's above the turning point, it touches once. If it's below the turning point, it touches also once. So we are looking at it now at where it's P in this case, not K. So here it's P greater than 18 or P less than -9. That is where it touches the turning point, or that is where it's below the turning point. It touches the graph once, also touching the graph once there. Which means that the trick with a third-degree function is that because it has 2 turning points, then you have to focus on one turning point and focus on the other turning point. Where this has 1 negative root, if you check here, if you check in between, as I draw these lines, how many roots do you have? You have 3, and all of them are on the positive x-axis. All 3 are on the positive x-axis. or you have 1, but that 1 root is on the positive x-axis. But if you focus on now 43 here, the y-intercept, if you put the line just above the y-intercept, what do you see? It now cuts the graph on the negative x-axis, which means that P now should be greater than 43. Moving very quickly through this, but it is the same concept. It's just that now we are applying it with third degree functions. Right, I'm going to move on. Now, using a factor theorem to solve a third degree polynomial, we want to use a factor theorem to solve this polynomial. I'm just going to run quickly through this. Right, the first thing that we need to do here, we want to solve for x and we have a third degree function or polynomial in this case. We use the factor theorem. So we should, by trial and error, try to find the factor. How do you work out the factor? You look at the last term. So the factors of the last term, it's plus minus 1, plus minus 2, plus minus 3. Those are the factors of the last term, 6. So we're going to try those factors out in our calculator, starting with minus, going to positive, or positive to negative. I'm going to start with negative 1. If I use 1, I'm going to start with 1 cubed minus, in my calculator, 2 into 1 squared minus 5 into 1, and then plus 6. If I use positive 1, I get that the answer here is 0. So when x is equals to 1, the whole thing simplifies to 0, which means that x minus 1 is a factor. I've identified the factor. I have x minus 1 being a factor. Now, if I want to then simplify this, I can use two methods. Any of the two methods. I can use any of the three methods. It's long division, synthetic division, and inspection. But because of time, I'm not going to do long division. I'm just going to show you something on synthetic and something on inspection. But moving forward from this, I'm just going to use synthetic division. Now, by synthetic division, this is what I'm going to obtain. I'll have my factor, x minus 1 is a factor in this case. I'll have my factor here. The factor is 1 when I substitute x is equals to 1. Then I'll take the coefficients of all the variables in my equation. The coefficient of x cubed is 1. The coefficient of x squared is minus 2. Remember, if I did not have a value that contains x squared, the coefficient is going to be 0. So the coefficient of x is minus 5. The constant is plus 6. That's how I start with synthetic division. So the first value here is always 0. You always start with 0 there. So you add 1 plus 0, you get 1. 1 multiplied by the 1 at the top there, you get positive 1. And then you add again minus 2 plus 1. This gives me minus 1. Minus 1 times the 1 at the top there, or times the factor, I will get minus 1. So minus 5 minus 1, that's minus 6. Minus 6 times 1, I get minus 6. So the last one should always give you 0. Then you'll know that your synthetic or the use of synthetic division is correct in this case, because the last term or the constant term should always be 0. Now, from here, I can then say this is x minus 1 into, obviously, this is the coefficient of x squared. This is the coefficient of x. That's the constant is equals to 0. This I know is x squared. This is x, and that's the constant. So coefficient of x squared is 1. Coefficient of x is 1. And the constant is 6. So I can continue and factorize this. If I use the trifactor method, I have that x and x there. And then I have 3 and 2. The bigger one should be negative. 2 should be positive. So x is equals to 1 or x is equals to 3 or x is equals to minus 2. That is through synthetic division. I found the values of x. However, I can also use inspection. By inspection, if I want to use inspection, what I'm going to do is I'm going to take my factor x minus 1, repeat it 3 times, x minus 1, x minus 1. Then I equate that to 0. Then by inspection, I'm going to look at what I should do to get x cubed as the leading variable. I start on the first bracket. To get x cubed, I must have x squared. If I multiply, distribute throughout, I'll get x cubed. I'm okay because I've done that. And then I focus on the last term, positive 6. In order for me to get positive 6, I must multiply negative 1 with negative 6. If I multiply negative 1 with negative 6, I'm going to get positive 6. Now that I've looked at the first term and the last term, I'm now going to use a distributive law. I distribute the x squared. If I distribute here, I get x cubed minus x squared. Then I'm going to ask myself, I have on the equation, I have minus 2x squared. I have minus 2x squared, and here I have only minus x squared. In order for me to have minus 2x squared, I need a minus x, because this minus x times that would give me minus x squared, which would give me minus 2x squared. If you've done that, the 5 would take care of itself. Now that I've worked out my inspection, I'm going to then group this using the method of grouping. I take one bracket out of the 3 brackets, and then I take the terms outside of the brackets and create a bracket for them. That is how you group. That's equals to 0. So all the terms that are outside the bracket, I've created a bracket for them and I put them in there. If you check this, it's exactly the same as that. So I won't continue and factorize this any further because it's the same as that other one. Right, that is the use of the factor theorem to find the values of x. Right, this was supposed to be your activity, but because of time, we won't be able to do it. Let's look at the graph of a cubic function. Let's look at the graph of a cubic function. Now here, we are going to focus on the graph of an equation ax cubed plus bx squared plus cx plus d. We are saying that the cubic function can have up to 2 stationary points. It's not always the case that you'll have 2 stationary points, but you'd have at maximum 2 stationary points. And all cubic graphs have 1 point of inflation. All of them would have 1 point of inflation where the concavity changes. Now, if a is greater than 0, these are possible shapes of the graphs. You'll get, if you have 2 stationary points, then this is the graph that you're going to get. If you have 1 stationary point, then that stationary point would be a stationary point of inflation. But if you have no stationary point, that's what you're going to get, only the point of inflation. So these shapes are very, very important. Right, let's check when a is less than 0. When a is less than 0 and you found 2 stationary points, then this is the shape that you're going to have here. But if you found 1 stationary point, then that's what you're going to have. You call that stationary point the stationary point of inflation. And then if you don't have any stationary point, then you're going to just have that point of inflation. Now from this you can see that the shape of the graph depends on the number of stationary points. So it is advisable, if the question is not scaffolded in the exam, it is advisable to start with the stationary point, unless if the examiner has given you direction as to how to work with it. But if you are just given an equation and asked to sketch the graph, it's advisable to start with the stationary points, because from there you can be able to determine the standard shape. Right, these are the steps that we can use to sketch the cubic function. Step 1, determine the coordinates of the stationary points by differentiating the original function and equating it to 0. And then from there, you substitute the values of x that you obtained in the original equation to get the corresponding values of y. And then step 2, you consider the sign of A and determine the general shape, because you now know whether you have 2 stationary points, 1 stationary point, or no stationary point. So you can be in a position of determining the shape. Step 3, determine the x and y intercept, obviously, by putting x to be 0 if you want the y-intercept, putting y to be 0 if you want the x-intercept. And then if asked, determine the coordinates of the point of inflation by taking the double derivative of x and equating it to 0, and then find the value of x, and then substitute it in the original equation to determine the corresponding value of y. And then you can plot those points and draw a smooth curve. Right, let's look at an example. Determine the coordinates of the turning point of this graph. So this is an example where we have to sketch the graph. So first things first, we want to determine the coordinates of the turning point. So to get to the stationary points, we get the derivative f dash x is equals to, if we differentiate this, we're going to get minus 3x squared plus 2x plus 8. That is how we differentiate. Obviously, we have to put the derivative at the stationary point. At the turning point, at the stationary point, the gradient f dash x is equals to 0, which means that now we're going to have minus 3x squared plus 2x plus 8 is equals to 0. Now, if you divide by minus 3, you get 3x squared. You get 3x squared minus 2x minus 8 is equals to 0. You find the factors of this using our trial and error. So this is 3x and this is x. We're looking for the factors of 8. In this case, that would give us the middle term, which is 2x. We're looking for the factors of 8 that are going to give us the middle term, which is 2x. So we're going to use 4 as well as 2. So if you multiply here, you can see it's 3x squared plus 6x minus 4x. So we need our 4 to be positive and this one to be negative. So x in this case would be minus 4 over 3, or x would be equals to 2. Now, if you go back to the original function and substitute f of minus 4 over 3, then you make use of your calculator. Where you see x, you put minus 4 over 3. If you work that out, it will simplify to minus 500 over 27, which means that the coordinate here would be minus 4 over 3 is to minus 500 over 27. This we can approximate because remember we'll be drawing it on the set of x's. So if we approximate this, this is negative 1,3 and this one is approximately negative 18.5. We found the first stationary point. The second one, what we're going to do is we're going to substitute the value of x. In this case, we obtained x is equals to 2. We substitute that value of x in the original function. If we substitute 2, we're going to get 0. So we have that the other stationary point in this case would be 2 is to 0. So we have 2 stationary points. Because we have 2 stationary points and a here, if you check, a is equals to minus 1. So a is negative. If a is negative and you have 2 stationary points, then we're going to get this shape because we have 2 stationary points. Right. So our shape in this case would be this way because we have 2 stationary points and a is negative. Right, moving right along, we've just determined our stationary points. How did we do that? We found the first derivative, equated it to 0, solve for x, use those values of x to find the corresponding values of y. Right, moving on, calculate the x and y intercept. So we're going to start with the y-intercept. So y-intercept, how do you find the y-intercept? Let x to be equals to 0, or put x to be equals to 0. If x is equals to 0, then f of 0 would be minus 12, which means that y would be minus 12. That would be our y-intercept, minus 12. So the coordinates of the y-intercept would be 0 and minus 12. Now, we need the x-intercept. We know that for x-intercept, we let y to be equals to 0. If we let y to be equals to 0, then we're going to have a 0 here. So we have minus x cubed plus x squared plus 8x minus 12 is equals to 0. So if that is equated to 0, then we need to then find our factor, because this is now a third degree equation where we want to solve for x. And to solve for x here, we need to find the factor of this particular equation. Now, if you are to substitute plus minus 1, you won't get a factor if you substitute in your calculator. If you are to substitute plus 2, you're not going to get a factor. But if you put minus 2, then you're going to get a factor. Or rather, if you put positive 2, you're going to get a factor. If you put minus 2, you're not going to get a factor. So x minus 2 is a factor. X minus 2 is a factor because if you substitute x is equals to 2 in the equation, you get 0. So we're going to use synthetic division again here, because our factor in this case is 2. And then I write down the coefficient of all the variables. Coefficient of x cubed is minus 1. Coefficient of x squared is plus 1. Coefficient of x is plus 8. The constant is minus 12. So that's what you do with synthetic division. If I start at 0 here, minus 1 plus 0, that gives me minus 1. Take the minus 1, you multiply by the factor there, I get minus 2. So 1, then I add 1 plus minus 2, I get another minus 1. Minus 1 multiplied by the factor there, I get minus 2. And then plus 8 minus 2, I get plus 6. Plus 6 multiplied by the factor there, I get plus 12. So if you add the 2, you should always get 0. So I'll have that the factor is x minus 2 into minus x squared minus x plus 6. This is equals to 0. Now quickly, we can divide by negative uniformly or take out negative as a common factor. So we have x minus 2, x squared plus x minus 6. This is equals to 0. If you find the values here or you factorize x squared plus x minus 6, obviously we look for the factors of 6. In this case, that would give us 1. We look for the factors of 6, that would give us 1. We would have 3 and 2. The bigger number should be positive, so 3 is positive, 2 is negative. So from here, we get that x is equals to 2 or x is equals to minus 3. So these are our roots or the values of x, the x-intercept. 2 is to 0 and minus 3 is to 0. So now we have the x and the y-intercept. We can move on to the point of inflation. Remember, with the point of inflation, we want to solve the equation f double prime of x is equals to 0. That is where the point of inflation occurs. So we find f dash x. F dash x, the derivative of f with respect to x is minus 3x squared plus 2x plus 8 minus 3x squared plus 2x plus 8. And then if you differentiate this for the second time, if you differentiate it again, obviously we get minus 6x plus 2. So we put f double prime of x to be equals to 0. Then we're going to get that 6x is equals to 2. Then x would be 1 over 3. X would be 1 over 3. That would be our point of inflation. Right, I want to then determine the y value if the x value is a third. So f of 1 over 3, we substitute the x value in the original equation to get the y value. So f of 1 over 3 in this case would simplify to, if you use your calculator, you'll get minus 250 divided by 27. Minus 250 divided by 27. So the point of inflation in this case would be a third is to negative 250 divided by 27. If we approximate this, this would be 0.3 to minus 9.3. Right, that is the information that we have. And now we want to sketch the graph. Now we want to sketch this graph. We are using all the points that we just got, and we want to now sketch the graph. Now sketch the graph of f, indicating all intercepts with the axis as well as the turning points and the point of inflation. So we want all those parameters there. Now, we're going to start. I have my Cartesian plane in this case. Now, I'm going to start off with the scale for the x-axis. You can use different scales. Obviously, I have my x values is 2 as well as 3. So I'm going to use scales of 1, minus 1, minus 2, minus 3, minus 4, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4. So I'm using scales of 1 in my x-axis because when I check my x-intercept, the x-intercept range between 2 and minus 3. And then on the y-axis, I have that I have the turning point being 12. I have a value approximated at minus 18.5 for another turning point, and I have minus 9.3. So I would just use scales of 4 here. I have 4, 8, 12, 16, 20. Also here, minus 4, minus 8, minus 12, minus 16, minus 20. So minus 20, minus 16, minus 12, minus 8, minus 4, 4, 8, 10, oh no, 4, 8, 12, 16, 20. Sorry, made a mistake there. Now I'm going to start with my stationary points. My stationary points there were given as, remember, I got 2 is to 0, and I also got minus 1.3 is to minus 18.5. So I'm going to start there. 2 is to 0 is my stationary point. I have a point there. And then I have minus 1.3. X is minus 1.3 somewhere here when I approximate it. And then it should be matched with minus 18.5, which is almost minus 19. So it's going to be approximately here. So that's what I'm going to have. Minus 1.3 and minus 18.5. And then I have my y-intercept at minus 12. And then I should also trace my point of inflation. Point of inflation, we said, is 0.3 is to minus 9.3. So 0.3 for x is somewhere here. And then we trace minus 9.3 somewhere here. So this would be my point of inflation. And then my last turning point in this case would be 2 is to 0. 2 is to 0. And then the graph, I made a mistake here and said it turns at minus 2. It does not turn at minus 2, it turns at 2. And then here, if you check, I have minus 3 as the x-intercept. So the graph should intercept at minus 2, minus 3, it should intercept here, but it should turn at this point and that point. And remember, we said the graph should exhibit this shape. That is the general shape that we came up with. So I would start here, the graph intersect minus 3, and then it turns here. Remember, after turning there, it should intersect y at minus 12. It intersects here at minus 12, changes concavity here, and then intersect at 2, or rather turns at 2, forms a tangent there, and then that would be my completed function. So I have my turning point, coordinates of the turning point here is minus 1.3, minus 18,5, and then I have here 2:0. So that would be the graph here. That would have two stationary points in this case here, which is concave up, and then another one which is concave downwards. Right, I want you to take a picture of this, but before you take a picture of the activity that I have for you, it's a homework activity, you can take a picture of that whilst I summarize what we did with sketching a third degree function. Remember, I said it is important to note that we should always start with the stationary points because they directly give us the shape, unless if the examiner has led you to questions that they want you to answer, like in this exam type question. But if they just gave you an equation and they asked you to sketch, start with your stationary points. Your stationary points, the number of those stationary points, if you get 2x values, then you know you're going to have 2 stationary points. If you get 1 x value, then you know that you're going to have 1 stationary point, and that stationary point will also be a point of inflation. So it will be called a stationary point of inflation. After finding the turning points or the stationary points, you find the x and y intercept, you find the point of inflation, and then you are going to be in a position of sketching the graph, focusing also on the shape. So there is an exam type question that I want you to try out. You can take out, or rather you can take a picture of this question, try it out in your spare time and see how you can draw that particular function. I think it covers everything that I just touched on as far as third degree functions are concerned. Right, grade 12s, we unfortunately have run out of time for today's lesson. Remember to sanitize, to wear your masks, and to always practice mathematics. See you next time. Bye-bye.